All right, next up we have chemical analysis of gases, so further applications of the ideal gas law. So let's jump right into some examples. Example 1212 on page 416. Read along, please. It says a 0.109 gram sample of a pure gaseous compound occupies 112 milliliters at 100 degrees Celsius and 750 torr. What is the molecular weight / molar mass of the compound? So we've seen something like this before where we were asked to determine the molecular mass or molar mass of an unknown substance. So if you recall, in order to determine the molar mass of an unknown substance, we take the mass of the substance, which is given to us in the problem, and we divide it by the moles of the substance. So how we find moles is different in different types of these problems. So in this case, we know the volume of a gas, we know the temperature of a gas, and we know the pressure of the gas. Knowing all of that, we can find moles by using the ideal gas law. So in the book, if you take a look at the top of the next page, it sets it up into 2 steps. Use the ideal gas law to find moles first, and then second step, take the grams of the substance divided by the moles that was calculated, and you get your molar mass. Number 1213, example 1213. Again, same idea. We're looking for molecular mass. So still given temperature, pressure, and volume. The only difference between these two problems is that in 1212, the pressure is given in torr, which is fine. We can either convert that to atmospheres and use 0.0821 for R, or we can just use 62.4 and leave it in torr. And then in 1213, we're given the pressure in atmospheres, so definitely going to use the 0.0821. All right, turn to page 440, and there's a problem just like these examples. Go ahead and do number 51 now. So as you can see, I decided to do it all in one shot, so I took the mass of the gas divided by, so all of this here on the bottom is this. I use the ideal gas law, plugged in PV over RT. That'll give us moles. And we end up getting 71.1 grams per mole or 71.1 AMU. So what is the possible identity of this gas? So when it says suggest the identity of the element. So this is some gaseous element. So what has a molar mass of about 71 grams per mole? If we look in the periodic table, you might think, I don't know, germanium or gallium. Neither one of those are gases. Krypton, that's the 83. Bromine's close to, nope, that's 80. We want 70. So this is probably chlorine. So chlorine has a molar mass of about 70.9 grams per mole or 70.9 AMU for the molecular mass. All right, let's go ahead and try number 53 this time. Same type of problem. We're looking for molecular mass and identity of the substance through molecular mass. Go ahead and do that now. Pause the video. As you can see, I tried a different approach this time, broke it up into 2 steps, found moles first, then took the grams of the gas divided by moles, and we get 44.0 grams per mole. Any idea what this could be? Any familiar with any substance that has a molar mass of 44 grams per mole? Maybe carbon dioxide. That has a molar mass of 44.0 grams per mole. All right, let's take a look at the next example. So we're going to take it a step further, and this time we're going to determine the molecular formula of a compound. So it says an additional analysis of the gaseous compound in 1213 showed that it contained 54.5% carbon, 9.10% hydrogen, and 36.4% oxygen by mass. What is the molecular formula? So first thing we need to do is to determine the empirical formula. If you turn the page, we'll see that. So take those percentages, convert them to grams like we've done before. Assume you have 100 grams of the compound. So you'll have 54.5 grams of carbon, 9.10 grams of hydrogen, 36.4 grams of oxygen. Now the book shows it set up a different way. I don't really recommend this way. It just looks a little different than what we're used to doing it. So follow the correct steps, use your conversion factors. Empirical formula is C2H4O. Next step is to determine the mass of the empirical formula, which is 44.0 AMU. And according to 1213, the molar mass is 88.0. So take 88.0 divided by 44.0 and you get your multiple. So the molecular formula is twice the empirical formula. So we get a molecular formula C4H8O2. So kind of a combination of old and new material determining empirical formula. This time, instead of being provided the molar mass or molecular mass to determine molecular formula, you need to first calculate the molar mass, and then you can use that to find the molecular formula. All right, number 55, page 440. Have fun. Setup, of course, you want to show all of the work in determining the empirical formula, but I'm confident that you can do that, so I just skipped ahead to the empirical formula CH2, calculate the mass of the empirical formula, 14.0 AMU, and then our next step is to determine the molar mass. So this time we're given density. So density at STP. So here's what I did. To determine the mass of a gas, we need to know the density and the volume. So given the density, STP. So what is the volume in liters of 1 mole of a gas at STP? That is 22.4 liters. And so notice the work I did here to find the molar mass. Ultimately, we get 56.0 grams per mole. Take your molecular mass divided by the empirical formula mass to get your multiple. This time is 4. So the molecular formula is 4 times the empirical formula. So we get C4H8. All right, changing gears to Dalton's law of partial pressure. Suppose you have a mixture of gases. In a mixture of gases, each gas exerts its own pressure. So remember, pressure is caused by collisions of gas particles with the walls of their container. So depending on how much of each gas there is, each gas may have a different pressure, has its own pressure. This is called partial pressure. So according to Dalton's law, the pressure of a mixture of gases is simply the sum of the individual or partial pressures of the different gases in the mixture. Take a look on page 419. So we have gas A has a certain pressure. So we have mercury in that tube. So the pressure of the gas pushes on the mercury and pushes it up inside the tube. So pressure of gas A is PA. Gas B, pressure of gas B is PB. Take gas A and gas B, mix them together in the same size container as what they originally were. So we get a mixture of A and B. And according to Dalton's law, then, the total pressure of that mixture is simply the sum of their individual pressures. So PT equals PA plus PB. Pretty much as simple as that. All right, example 1215 at the bottom of the page there. Read along. It says a 10-liter flask contains 0.200 moles of methane, 0.300 moles of hydrogen, and 0.400 moles of nitrogen at 25 degrees Celsius. What is the pressure in atmospheres inside the flask? So you have a mixture of gases. They give you the amount of each gas, and we want to determine the pressure. We are also given, besides the amount of each gas in moles, the volume of the container and the temperature. So we can use the ideal gas law to find the pressure. Now, you don't need to do the ideal gas law for each gas separately. That's a lot of work. So instead, just add up the moles to get the total amounts of gases inside the container. 0.2 plus 0.3 plus 0.4 is 0.9. 0.900 moles. Plug that into your ideal gas law and solve for P, and we get 2.20 atmospheres. What is the partial pressure of each component in the mixture? So now this one is going to require a little bit more work. So now, this time, we do have to do ideal gas law separately. So use the moles of each gas, plug that into the ideal gas law, and you get the partial pressure of each gas. I'll show you a trick later on that will help you avoid having to do this method. We're using the ideal gas law in this case 3 different times. All right, take a look at number 57 on page 440. Let me walk you through. It's just a bit just to get you going in the right direction. A sample of oxygen of mass 24.0 grams is confined in a vessel, a container, at 0 degrees Celsius and 1,000 torr. All right, so what do we know? We know the amounts of the gas, we know the temperature, we know the pressure. We can use the ideal gas law to find the volume. So what is the volume of the container that this gas is in? We need to know that for the next part. Continuing on, it says, then 6.00 grams of hydrogen is pumped into the vessel at constant temperature, meaning the temperature is still 0 degrees Celsius. What will be the final pressure in the vessel, assuming only mixing with no reaction? All right, go ahead and pause the video and try this one out. All right, so here it is. I just did all in one shot here. So again, got to find moles of oxygen and moles of hydrogen. We got to combine those to add those up. You can do that separate calculation if you want. Plug in moles total here if you want. Notice I used a different R this time because I just want to do a comparison with the original pressure, which was given in torr. And then temperature says does not change, divided by our volume, which we calculated in the first parts, as you can see there, 12.8 liters. And we get 4,950 torr. So with the oxygen itself, the pressure was 1,000 torr. Add just 6 more grams of hydrogen, which is nearly 3 moles. So it's a lot more gas that you're adding, and the pressure goes up almost 5 times. So notice that. Start off with less than a mole of gas. I think 24 grams is 0.75 moles. Add 3 more moles of gas, and so that is 4 times the amount of gas that you're adding. So we have, 5 times the amount of gas as what you originally had, and you get nearly 5 times the pressure. Interesting. Which leads us to mole fraction. So that looks like an X. That's actually Greek letter chi, capital letter. So it says the partial pressure of a gas in a mixture is equal to its mole fraction times the total pressure. So let's do this. I'm going to kind of write it in reverse. The pressure of a gas, an individual gas, partial pressure, is equal to the total pressure of all the gases in that mixture times the mole fraction of that gas. So again, each individual gas has its own pressure. How much of the total pressure a gas exerts is proportional to the number of particles of that particular gas. And so we can see that here we have a direct relationship between the mole fraction, which I'll show you how to calculate that in a second, and the partial pressure of the gas. The greater the amount of one of the gases, the greater its partial pressure. And the opposite is also true. So let's do this. Let's go ahead and write an equation to calculate mole fraction. Mole fraction is kind of like a percent, except we don't multiply it by 100, we leave it as a decimal. So I'm going to say mole fraction of gas A we find by taking moles of gas A and dividing it by the total moles. So it's kind of part over whole. And leave it as that. Don't times it by 100. So like essentially it's the same thing as percent though. So let's say gas X there's a percent, 30% of the particles in a container are gas X. Well, what's percent of the total pressure do you think gas X will exert? Well, 30%. So kind of makes sense here. So that's how we do that. So mole fraction, moles of one gas over total moles, that goes here. If we multiply the mole fraction by the total pressure, we get the partial pressure. Likewise, something else that we can do with this equation is rearrange it. If we know the partial pressure of a gas and we know the total pressure, we can use that to find the mole fraction. Or if we know the partial pressure of a gas and the mole fraction of that gas, we can find the total pressure. So we can solve for any one of these three things here. But this one here is a useful relationship if we're not given the amount of the gas, and so we can't calculate moles. We can use a partial pressure of the gas and the total pressure, and that will give us our mole fraction. All right, let's take a look on page 421. It says calculate the mole fractions of the three gases in example 1215. So remember we had 0.200 moles of methane, 0.300 moles of hydrogen, and 0.400 moles of nitrogen, which gave us total moles of 0.900. So pretty easy. Just take the moles of each gas divided by the total, and we get our mole fraction. So mole fraction for methane, 0.222, hydrogen, 0.333, and nitrogen, 0.444. Interesting numbers. Or, as I explained earlier, we could use the partial pressure of each gas, which was calculated in that example, and the total pressure, and use those to find the mole fraction. So the partial pressure of the methane, if you look at the top of page 420, was 0.489 atmospheres. And if we look at the bottom of that solution in 420 there, the total pressure was 2.20 atmospheres. So take 0.489 atmospheres, it left off the unit there in the book, divided by the total pressure, 0.220 atmospheres, and look at what you get, 0.222, same as what you got by dividing moles. So either way is fine. All right, number 59 on page 440. Go ahead and work that out. Pause the video now, please. So kind of an interesting problem here is we're really not dealing with mole fraction or anything like that. I guess you could, but that's more work. So we're given the partial pressure of each gas. It just asks for the ratio. So let's take one divided by the other. We get a ratio of 1 to 4. This is a mole ratio because mole represents a certain number of particles. It's also a ratio of the number of molecules as well. 21, look at 1217, read along. The mole fraction of oxygen in the atmosphere is 0.2094. Calculate the partial pressure of oxygen in air when the atmospheric pressure is 760 torr. So use the equation I gave you before. Total pressure times mole fraction equals the partial pressure. You can see the answer on the bottom of the page. All right, 1218, a little different. Two tanks are connected by a closed valve. Each tank is filled with the gas as shown, and both tanks are held at the same temperature. And it looks like they have different sizes. We have 5 liters for tank A, 3 liters for tank B. When we open the valve and allow the gases, to mix. Letter A, after the gases mix, what is the partial pressure of each gas? So what happens is when you open that valve, the gases are going to diffuse. Some oxygen is going to move from tank A to tank B. Some nitrogen is going to move from tank B to tank A. And so basically, both gases then are going to occupy the entire volume of both tanks, which would be 8 liters. So take a look at the solution. It says for oxygen, we have, we're going to use Boyle's law. We know the volume and pressure of the oxygen when it's just in tank A. The volume is going to increase from 5 liters to 8 liters. And so if the volume increases, the pressure will decrease, and we see that the pressure decreases to 15 atmospheres. You could do the same thing for nitrogen. Again, its volume will increase, this time from 3 liters to 8 liters, and so the pressure is going to go down. Letter B, what is the mole fraction of each gas in the mixture? All right, so we can take the partial pressure of each gas and divide by the total pressure. First, we need to find the total pressure. So 15 and 12 atmospheres gives us 27 atmospheres. Take partial pressure divided by 27 atmospheres, and we get the partial pressure of each gas. There's another way to do this, which involves more work, but we don't need to do that, so we'll just stick with that solution. This time I'm not going to have you do number 61, but I'll walk you through it a little bit, so take a look there. It says assume that unpolluted air has a composition shown in table 12.2, that's on page 400. Calculate the number of molecules of nitrogen, oxygen, and argon in 1 liter of air at 21 degrees Celsius and 1 atmosphere pressure. All right, so we see looking at the table, percentages by volume. This is also percent by number of particles, since in total they're going to exert the same amount of pressure. Each gas will have its own pressure, but we can make that relationship between the number of particles and volume. So 78.9% of the air we breathe is nitrogen by volume, also by number of particles, or in this case, we can also, actually, let's back up a second. That is the percent by volume. It's also percent by number of particles. We can use that percentage also then to determine the partial pressure. So if 78.09% of all the particles are nitrogen molecules, that means that 78.09% of the total pressure is exerted by just nitrogen. So it says 1 atmosphere of pressure. So the partial pressure of just the nitrogen is 0.7809. So we can plug that in along with the volume, which is 1 liter, along with the temperature, 21 degrees Celsius, 294 Kelvin, into the ideal gas law and find moles. From moles, we can use that to find number of molecules using Avogadro's number. So I just want to point out a little different problem there. All right, next, different application of Dalton's law. It says some gases are collected over water. So it kind of needs 2 blanks there. Over water, or over a water solution. Consequently, the measured pressure is the pressure of whatever gas you are collecting and any water vapor that has evaporated with the gas. So if you take a look on page 441 at question number 63, we see a gas is being produced in the container on the right. You're bubbling that up into the container on the left. And so that gas is being collected over water. Well, that water is going to evaporate and contribute to the total pressure inside that container. So if you go to page 423, you'll find a table of vapor pressure of water at different temperatures. So first of all, notice as the temperature of water increases, so does the vapor pressure. Hopefully that makes sense. As the temperature increases, the rate of evaporation increases, and therefore the vapor pressure of the water will also increase. So we'll need those values. If it's not in that range, there's a table in the back of the book that has more vapor pressure water at different temperatures. All right, so on that same page, 1219. Oh, let's write an equation. So anytime you collect a gas over water, we can use this. So PT, the total pressure, is equal to the partial pressure of the gas plus the vapor pressure of water. And again, at a certain temperature, that is a constant. So often we know the total pressure and the vapor pressure of water. We can use that to find the partial pressure of the gas. And that's what we're going to do here. 1219, hydrogen was collected over water. You did this in Chem 1, actually. At 21 degrees Celsius, and the pressure is 748 torr. Now, what it doesn't tell you is that the 748 torr is the pressure of both the hydrogen and the water vapor. The volume of the gas sample collected was 300 milliliters. And again, that volume is for both gases. How many moles of hydrogen were present? How many moles of water vapor are present? And so on. So take a look at the solution. Vapor pressure of water at 21 degrees Celsius, if we look at the table, is 18.65. The book just rounded up to 19 for some reason. So take the total pressure, 748, subtract the vapor pressure of water, and that'll give you the pressure of just a hydrogen, 729 torr. And then they take that and convert to atmospheres. Turn the page. We know the pressure of the hydrogen, you know the volume of the hydrogen, you know the temperature of the hydrogen. You can use that to find moles of hydrogen. Letter B in the solution, finding the moles of water vapor. So we know the pressure of the water vapor, we know the volume, we know the temperature. We can use that to find moles. And then if we take moles of one gas over moles of total gases, we can find the partial pressure of each gas. And then lastly, letter D, it wants us to find grams of hydrogen, take the moles of hydrogen and converts that to grams. All right, go ahead and work on exercise 63 on 441. Go ahead and pause now. Be careful now that 757 torr is the pressure of the hydrogen and the water. And so we need to use the vapor pressure of water at 19 degrees Celsius, which according to the book is 16.5 torr, and subtract that. Don't forget that. That's really important. Solve for moles, 0.00143 moles. Now you could do this the hard way or the easy way. I would say the hard way is to take the moles of hydrogen and plug that back into the ideal gas law using standard pressure, which is 1 atmosphere, and standard temperature, which is 273 Kelvin, and you can get the volume that way. Or you can use, as I've shown here, the standard molar volume of a gas at STP as a conversion factor. So find moles of hydrogen, and then we're going to multiply that by 22.4 liters per mole. And to get our volume, I converted that to milliliters, 32.0 milliliters. All right, so that concludes this lesson. Thanks for watching.